So we've come to the point where we've talked about the KKT conditions a bunch now. We know what they are, and so it's now time to prove them. So the proof is quite involved, as you'll see. But here's what we're going to prove. So let's just remember what the theorem is. So we have a bunch of conditions here, and then the idea is that a necessary and sufficient condition that x star is a minimizer of f over some convex set, omega, is that there exists a solution to this big system of equations that we've got written here. So this is an if and only, there's a necessary and sufficient condition here. So this is an if and only if theorem, so we need to prove this in both directions. So we need to prove that if x is a minimizer, then it satisfies those equations. We need to prove that if a point x satisfies those equations, that it is a minimizer. So we need to prove it in both directions. And we have a few pieces of information that we can use in both directions. So the theorem has a bunch of conditions that I've circled here. So f is convex. All the GIs that form the constraints are convex. We have the set omega, which says that it's all the points for which gi of x is less than or equal to 0. That's the one in the middle there. And that set omega has got to be non-empty. So there's 4 bits of information. We're going to need to use all of these to prove this theorem in both directions. So here's what we're going to do. So this theorem's a bit involved. So what I'm going to do is I'm going to do a trick that we've done before, which is to annotate the proof rather than going through it all on the board. So on my little piece of paper here, I've just written out all of those conditions that we have about the theorem. And I was thinking we might just keep track of when we use each of these. So there's 4 bits of information that we can deploy at any point. So we've got that f's convex, all the GIs are convex, the GIs are less than or equal to 0, and the interior of this convex set omega is non-empty. And we're going to prove this in the sufficiency direction first. So we're going to go backwards, and then we'll do the necessity direction, which is harder. So let's start with the sufficiency. Okay, so here's the proof. And we're proving that first, that if I satisfy the KKT conditions, if I satisfy those equations, then x is a minimizer, right? So the KKT conditions imply optimality. So where do we start with this? So, the bits of information that we have here are that my functions are convex. We have a lot of information about convexity, right? And so that's what I'm going to use. So the starting point for this, as it so often is, many times in this course, is that we use facts about convexity, right? So first, the first thing that I know that I can use is that my function f of x is convex. And in fact, our starting point here, this is the theorem that says convex functions lie above their tangent planes. And that's a statement of a theorem back from chapter 3, so theorem 3.14, right? And we're just writing that down. So we start from there, and then I'm going in the direction here where I'm assuming that the KKT conditions are true, and I need to prove that x star is a minimizer, right? So I'm assuming that I've got the KKT conditions here, so I can substitute them in, right? So the first KKT equation, the big interesting equation at the top, says something about the gradient of f. The gradient of f is equal to negative of this sum of lambda times the gradient of the GIs. So we can plug that in and then rearrange. So all I'm doing in these 2 lines here is I'm subbing KKT1. Right? I'll call that KKT1 because it's the first KKT equation. We plug that in. And so now, to be able to go further here, right, I need to show that x is a minimizer. And if I look at this, let's write this second line here again. Here, this statement says that f of x for any x is greater than or equal to f of x evaluated at this minimizer, subtract something, right? So to show that x star is a minimizer, I need to show that f of x is bigger than f of x star, right, for all x. Right? That's what it would mean for x star to be the minimizer. So really, I need to show that the negative of this thing here, that whole thing is positive. So in other words, I need to show that that expression there inside the sum, we need to show that that's negative. This is less than or equal to 0. And then I'd have f of x star plus something positive is less than or equal to f of x, which would mean that f of x star is the minimizer. So I need to show something about this expression here, right? So I need to say something about these GIs, right? And I need the gradient of GIs. So the rest of the game here is about getting some expression for the gradient of GIs. So what can I say about the GIs? Well, I know that the GIs are all convex. That's one of my other pieces of information that I can use. So let's use that. Right? So all we're doing here is we're writing down, this is the expression of a chord through GI, and I have this result that GI on this chord is less than or equal to 0. So the reason for that, let's draw a little picture of a GI here. What am I doing? Right, I'm taking a chord through that function. GI is a convex function, which means that it sits below its chord here. I also know that all my GIs are less than or equal to 0, right? So if GI is convex and sits above this chord, and it also sits below 0, then GI evaluated on this set of points here must be below 0. Right, so really, we can add in a little bit more information here. We know that this is, because GI is convex, we know that I can write 1 minus x of g star plus t g of x. And now t and 1 minus t are positive. My function g evaluated at any point x in the set is always negative, so that goes in there. So this really uses the fact that G is convex, and my GI of x are all less than or equal to 0. That's what that step uses. So I've got some information about GI, right? I don't need GI, I need the gradient of GI. So the next part of the game is to try and construct a gradient of GI, right? So that I can essentially plug into this. And that's what all this stuff is doing here. So this sequence of steps is all about constructing a gradient of GI. Sorry, I don't need that. GI is specifically evaluated at x star because that's what we need for up here. So multiplying by lambda I, subtracting lambda I times GI of x star, dividing through by t, and then taking the limit, doing those steps leaves you with that, right? And that's all got to be less than or equal to 0 by this inequality up here. And then as t approaches 0, what do I have? Well, this looks like the first principles definition of a derivative. Right, so what I just did was I constructed a derivative of g, a gradient of g from first principles. Right, so I did a bunch of operations. So I forced this into a derivative so that I could get a GI, right? So that I can match this up with that. And so what have I done? I've just shown here that the inside of that this object is always less than or equal to 0. That's followed from G being convex and negative, doing a bunch of operations. So I've shown that every term in this sum is negative. Right, so coming back up to this, I've now shown that f of x is greater than f of x star, subtract the sum of a bunch of negative terms, and so I'm done. Right? So f of x is always greater than f of x star, subtract sum of negative terms, and so that's greater than or equal to f of x star. And that's what it means for x star to be a minimizer. For any x, f of x star is less than or equal to f of x. So that's just shown that the KKT conditions imply optimality. So, interestingly, coming back to my little list of conditions here, what did I use, right? So to prove the sufficiency direction here, I used that f is convex, right? So that was the first line. I wrote down convex functions lie above their tangents for f of x. I definitely used that the GIs are convex, and I used that they're negative, so that I could construct my gradient of g. I didn't actually need to use that the interior of my convex set omega is non-empty. So interestingly, to get the sufficiency, to get that the KKT conditions imply optimality, I don't actually need to use that the interior of my convex set there is non-empty. So we don't need it in that other direction. Don't need it in that direction. We will need it in this necessity direction, in the forward direction. And so that's what we're going to do here. So that's the second part of this, so we're halfway done. The necessity direction is harder, and the proof is a little bit vaguer, omits a few steps here, or is a little bit brief, where it gives you a flavour of how this works. So this really is sort of an outline proof here. And the idea here is, the key idea is, this is where Farkas's lemma that we've talked about before really comes into play. Right, so here I'm proving in the direction that optimality implies the KKT conditions. So all I can use here, apart from these 4 bits of information, right, is that x star is a minimizer. So that's all I can use. So a little bit of extra, a little bit more difficult. I also need something new, which is this idea of a feasible direction. So let's start the proof here. Okay, so there's a definition of a feasible direction, right? So it's an epsilon delta definition for people who like that sort of stuff. Let me just talk about what this means. So a feasible direction is some at x within some set. So let's say we've got some set omega. It's a non-zero vector u such that so there's a point x, and the direction u is that there exists some delta where if I move along the direction of this u, so if I put a constraint in here, for example, so let's constraint on this set. If I move some direction in the some distance in the direction of u, right, I stay within the set. That's the idea here. And where this gets a little bit more complicated is that let's say I've got there my constraint is a straight line. If I've got some constraint, let's imagine that here's a cost function, and let me draw in a constraint that's curved now. All right, so if I draw in a slightly curved constraint, the constraint doesn't have to be a straight line. And so the idea is that if I take a point x here, if I move in the direction u, right, so the direction u that would be a tangent to that constraint. Right, and the idea is that if you give me some tolerance, delta, right, so you allow me some tolerance here, I can always find for all epsilon within that delta, I can stay. If I stay within this set. So if I move in this direction delta, I move off my constraint here, and eventually I'm going to move outside of my set omega, right? But the idea is that I can go a certain distance before I move outside of the set. And so that's the idea of the epsilon delta. So for there is some delta for which for all epsilon less than that delta, I stay inside the set. So the delta is this sort of tolerance. For staying within the set. So we need that idea, and then what we do here actually is we essentially work everything into the form of Farkas's lemma. So all we have to start off with is that x star is a minimizer. X star has got to be in this convex set, which gives me the final, which gives me the constraint from the KKT conditions that the GIs of X star have all got to be less than or equal to 0. So we get that straight away. So, okay. So, again, the conditions that I can use are my 4 basically about convexity and the non-emptiness of the set. So I start here by looking at the gradient of GI. So at this minimizing point, X star, let's look at the gradient, the negative gradient of GI, and that's got to point into my set. Right? We talked about that earlier. Yeah, my interior has got to be non-empty here, otherwise, well, there wouldn't be anything. There sort of wouldn't be anything to talk about here. There would be no set for this to point into. So we get to use that the interior of my convex set is non-empty straight away. Okay, and so now what we're doing is this is the same. We're using the convexity of G again. So because G is convex, we use the same. We use whatever results we have about convex function. So here again, I'm writing down something about convexity. So I'm using again the fact that convex functions lie above their tangents. That is a really common starting place for proofs in this field, because it's one of the things that I know. So I've got this expression here that the y minus x transpose times the gradient of g I evaluated at the minimizer has got to be less than or equal to 0. So that's using convexity for g, and then we, just as we did before, we'll do this. Write down what we know about the same thing for f. So because f is convex, we can write down the same sort of idea here. And so this works because x is a minimizer. X star is a minimizer. Okay. So we've got 2 expressions now for the gradient of g and the gradient of f. And now, so what we're doing now is all of these words, all of this stuff here is basically rewriting everything. So firstly, because this is a dot product and this is a dot product, I write them around in the other direction. And then, I'm doing some accountancy here. I'm defining these negative gradient of GIs for every I in my active constraints. So we write this as a matrix, right? And the idea of all of this is that we're rewriting those 2 statements essentially to make them look like Farkas's lemma. So to get from, so this stuff is the same as this stuff. It's just where we've introduced some notation about the A's and about the gradients of G and the gradients of F. And we've written this in linear algebra form. Okay? So, you can go through the details of that and make sure it's super clear. But really, it's just accountancy. And we introduce this feasible direction in terms of the stuff that we've got here, the y's and the x stars. And we're rewriting this all so that we can get to use Farkas's lemma. Right, so let's go back and remind ourselves what Farkas's lemma is. So it looks very similar to this stuff here, but what is it? So remember that it's this idea that if I have AX equals B, if that has a solution X for X greater than or equal to 0, then that has a solution for if and only if for every U, A transpose U is greater than or 0, then B transpose U is greater than or equal to 0. And if I come back to the picture here, that's exactly what I've rearranged things. This is what I've rearranged things to look like here. So we can apply Farkas's lemma, which says that I can go backwards from those statements to say that AX equals B has a solution, right? Except this is now A lambda equals B, and that's positive. So that's one of the KKT conditions. And my matrix equation here, A lambda equals B, is exactly, once I plug in the lambdas, when I plug in that A is the columns of A are negative gradient of GI, evaluated at X star, I get this expression here, which is exactly just my friend KKT1. Right? It's exactly just, we'll go back to the theorem. So there's Farkas's lemma. There's the theorem. It comes back exactly to this, where we've just pulled the, my AX equals B. There's the B. There's negative A times X. So the A's, things in the matrix A, are the negative gradients of GI, and the X's, the vector X, is that vector lambda. So really, it's all about just applying Farkas's lemma. And there is some intuition that we can get here. If I come back to this, what are we talking about with Farkas's lemma here? Remember that it's all about this idea of the convex cone, right? So if I have two vectors, A and B, and if I have two vectors A1 and A2, and I write down the linear combination, all linear combinations of those vectors where these coefficients x1 and x2 are positive, then I get this region here, right? And Farkas's lemma says that this vector B, any vector B, is either in the convex cone or there's this separating hyperplane. And now that we've got a little bit more intuition, we can identify these B's as the gradient of F, right? And the matrix A as all of these, having all of the gradients of these constraints. This is what it really links back to. So here's this AX equals B, or this A lambda equals B, right? Written out in equation form. So that's KKT1. And what this is saying, everything that it's saying is that if X star is a minimizer, then it has to be in the convex cone that you get from negative gradient of the constraints. Right, so if I create the convex cone from these gradient of GIs, which is this green region here, then if X star is a minimizer, it has to sit in that convex cone. And that's what we get from Farkas's lemma, or that's what KKT1 says. In the other case, where the gradient of F sits outside of that convex cone, it can't be a minimizer. It's the other way around. So really, the KKT conditions, Farkas's lemma, it's all saying, this is the deep intuition, or the deep idea here, that if X star is a minimizer, it's got to be in the convex cone. It's formed from the gradient of these constraints. If it doesn't, when I say it, I mean the gradient of F, gradient F of X at that minimizer has got to be in the convex cone of the gradient of the constraints. If not, it's not a minimizer. That's the big idea of Farkas's lemma. That's the big idea of the KKT conditions. So what we want to do next, now that we have the theorem, we have some idea of how the proof works, is we want to do a couple of examples, and want to talk about how we can use this to get some algorithms for actually solving these things. That's what we'll do next.